Okay, here is the review video for the chemical reactions test. Okay, so first things first, we talked, there's really two big sections of this test. Okay, the first one is types of equations and balancing, and the second one is stoichiometry. So I'm going to start with types of reactions and balancing. There are 5 types of reactions that we talked about. There's synthesis, decomposition, single replacement, and double replacement. Finally, combustion. Okay, a synthesis reaction is two things coming together to form one. Looks like A plus B goes to AB. The key to a synthesis reaction is there's only one product. Okay, decomposition is just the reverse of a synthesis reaction. It's A plus B falling apart, AB falling apart into A plus B. You only have one reactant for a synthesis reaction. Okay, for a decomposition reaction, excuse me. Remember that the reactants are over here on the left and the products are over here on the right. So synthesis and decomposition should be pretty straightforward. You are not responsible for predicting the products of a synthesis or decomposition reaction. However, single replacement and double replacement we're going to spend a little bit more time on because you are responsible for predicting the products. So single replacement looks like this. You've got something alone. It means it's an element. Maybe it's copper, silver, chlorine gas, Cl2, bromine, Br2, fluorine, F2, and something that's a compound, okay? HCl, AgNO3, something that's got 2 ions together. A wants B's date, so A and C end up together, leaving B out in the cold, okay? That is a single replacement reaction. Now, this reaction will only happen if, according to table J, A is more popular or more active than B. Okay? A is trying to take B's date, and that will only happen if A is more active or more popular in school than B is. If A is below B on the chart, then this does not happen. You have a no reaction, and that's all you need to write. Okay? Double replacement reaction is A and B. It's 2 compounds, and what happens is that A and C switch partners. So A ends up with D, and C ends up with B. It is really important that if it's written first over here, like A, it's written first on the product side. If C is written first on the reactant side, C needs to be written first on the product side as well. So you really are just switching their partners, okay? How do you tell if this reaction happens? You look at table F. If it produces water or something that's insoluble, we call that a precipitate. Water or something that's insoluble will give you a double replacement reaction. If you do not have water or something that's insoluble, you can just write NR, no visible reaction. That's like the types of reactions lab when we dropped those droppers on that clear sheet of overhead paper, and if you didn't see anything happen, it looked like you were just mixing clear liquids. That is a reaction that doesn't happen. Finally, combustion. Combustion is really easy. Okay, you're going to start with something that's got a lot of carbon and hydrogen, maybe an oxygen. And this part of a combustion reaction is always the same. Okay, it ends up with CO2 and H2O as your only possible products. Okay, so the water part and the carbon dioxide product, it also includes oxygen, right? If you're burning something, you need oxygen. If you put a lid over a candle, the candle goes out because it runs out of a reactant. So this part here is the same for any combustion reaction. If I asked you to write the combustion of methane or CH4, you would look up CH4. And then you would just finish it. You would go O2, arrow, CO2, H2O, and then balance it. If it was not methane, but ethane, that's C2H6. The rest of the reaction stays the same. O2 goes to CO2 and H2O, but your balancing will be different, okay? As far as balancing goes, what do you need to know about balancing? Balancing shows conservation of mass, okay? So it shows that there's the same number of things on both sides. So if I have something like this, this is the synthesis of sodium chloride. I need to have the same number of atoms on both sides. So here I have 2 sodiums, here I have 2 sodiums. Remember that it's like math. A big coefficient in front applies to everything after it, okay? But if you have something like this, NO3, and there's no parentheses, this 3 applies only to the O and not the N, okay? If it was this, then the 3 would apply to both, okay? So, balancing shows conservation of mass. So a common problem would be something like this. That's a synthesis of CO2, okay? If I want to, I might give you that there's 10 grams of carbon reacting completely with 20 grams of oxygen. How much CO2 is produced? You just have to set the mass equal to both sides. You will only have one unknown. In this case, I would produce 30 grams of CO2 because the mass before equals the mass after. All right, predicting products. There are really 3 types of products that you need to predict, but I already covered combustion. Remember, combustion, you just do plus O2, arrow, CO2, H2O, and then balance it. That's really important. Make sure that any reaction you give me is balanced. Make that your last step, okay? For single replacement, you're going to have something like this. Copper plus silver, nitrate forms what? Okay, first step, check table J. Is copper higher than silver? Yes, it is. Next step, if they're in the same column, they're going to replace each other. So silver and copper are in the same column, and nitrate's nowhere to be seen. So silver is what's going to be left alone. So you want to identify what's alone. Okay. Remember Haber-Finkel? Haber-Finkel. If it's any of those 7 elements that are alone, that means elemental, alone only, they all are diatomic. Okay? That does not mean that it's all of a sudden NaCl2. No. Okay? But if it was just chlorine gas, it would be Cl2. Okay? Chlorine alone. Once you identify what's alone, okay, then you need to flip-flop your new compound and balance. So my new compound here is going to be copper and nitrate. I'm going to kind of curl up this side here. I've got copper and I've got nitrate. I need to look up the oxidation states of both of them. Copper is +1, nitrate's -1, flip-flop, 1, 1, CuNO3. Now I go back and balance. Everything is balanced, so I am done. Okay? Double replacement is a little bit different in the sense that you're going to use the table F in this case, and you're going to use it as the last step, not the first step. Okay? So, first things first, we're going to have something like, let's come up with a good double replacement reaction. Sodium iodide plus silver nitrate. Okay? First step, write the first ones again. Okay? The first ones that I'm talking about are Na and Ag. Okay? So I'm going to write them, but I'm going to leave their partners behind. Okay? My next step is to switch the partners, okay? Actually, what you really should do first that I neglected to do, and I apologize, is find your polyatomic ions. How do you know it's a polyatomic ion? You look at table E, and you need to put them in parentheses. So here's a polyatomic ion that I'm going to put in parentheses. That's important because I want to know that that 3 is coming with me to the other side of the equation. If there was something that was not, if there was a subscript that was not part inside those parentheses, then I would drop it. Do not be a subscript dragger. Find my polyatomic ions and then rewrite my first ions again, okay? Step 3 is to switch places. So that means the iodine is going to end up with the silver, and the nitrate is going to end up with the sodium. Now, it's not NO. The 3 is in the parentheses, so the 3 comes with me, okay? If it was AgNO3 2, that 2 would not come with me because that's part of the formula, okay? I knew that was going to happen. That's part of the formula. And we have to write these formulas over here correctly, okay? So step 4 is going to be to flip-flop. Go look up your oxidation states. Sodium's +1, nitrate's -1, silver's +1, iodine's -1. So this one's actually pretty easy. Your 1 comes here, your 1 comes here, your 1 comes here, there. So everything is just 1, okay? If this silver for some reason was +2, this would be AgI2. It is just not that way for this example, okay? So this one's actually a +1. Step 5, Step 5 is to balance. Again, here's an example. Everything's balanced, okay? 1 sodium, 1 sodium, 1 iodine, 1 iodine, 1 nitrate, and 1 silver, 1 silver. Finally, my 6th step, 6 steps, can you remember that? Is to look at table F and find the precipitate. First thing I would do is look at those, there are 4 columns across on table F, okay? I would look at that 3rd column, and I'd see if anything applies to that 3rd column. That 3rd column are ions that are insoluble, and the exceptions are in the 4th column. So for example, OH minus hydroxide is insoluble. That means I'd circle it, except, and that's in that 4th column, when it's with group 1, when it's with calcium, strontium, or barium, okay? So then I wouldn't circle it if it was that exception. Table F is a little bit confusing, okay? But it's not impossible if you take your time and you read it. If you cannot find anything in that 3rd column, then I would suggest going to the 1st column and looking at everything that's soluble. Once you find everything that's soluble, I would take a look at the exceptions, which are the bottom 2 in the 2nd column. You can see that there's exceptions to the halides being soluble, and there's exceptions to the sulfates being soluble. One of the exceptions to the halides being soluble is with silver. And what happens is that we have this silver right here, silver iodide. Iodide is a halide, and it's with silver, therefore this is my precipitate. That means it is solid, insoluble. It is the solid, that milky solid that you see. Okay? That's how you know the reaction happens. If you do not have something to circle, there's no reaction. That's how you predict products. Finally, mold-to-mold stoichiometry. I'll do another one of these, okay? You guys are excellent at this, okay? So just don't get too far in your head because you guys are really good at this. What these coefficients are, these are moles, okay? They tell you how many sodiums do I need to react with, how many chlorines do I need to react with how many sodium chlorides. If I want to use, if I only have 1 sodium and I basically cut this one in half to 1, this one cuts in half to a half, this one cuts in half to 1. Okay, what I do to 1, I have to do to all of them. The best way to approach this is doing a proportion, okay? So you need to keep the ratios the same. Of course, I have to rewrite it now. You have to keep the ratios the same between all your products and your reactants. Now, if you care about what happens when the ratios are not the same, take AP Chemistry because we cover that right in the beginning of the course, okay? So, let's say if I have 5.6 moles of Cl2, how many moles of NaCl do I produce? Okay, here we go. First thing you need to do is find the molar ratio from your equation. Make sure the equation's balanced, number one. Number two, look at the things you care about, Cl2 and NaCl. My molar ratio comes straight from my coefficients. It's 1 Cl2 to 2 NaCl. This is your mole ratio. I don't have 1 mole of Cl2. I have 5.6 moles of Cl2. How many moles of sodium chloride do I produce? Okay. Now, this might be really easy to do in your head, but I would not all of them will be. Okay. So what I suggest you do is cross multiply. So I have 11.2 equals 1x. Divide both sides by 1. I get 11.2 moles of NaCl. Okay, that's how you're going to set up any of these problems. Okay, make sure when you do your proportion, if you have Cl2 on the top on one side, you keep Cl2 on the top on the other side. Keep that ratio the same. All right, good luck. You will all do wonderful.